Thanks for
we'd like to welcome Bane Vasic, who has been working in the area of coding for many, many years, including his famous work on finite alphabet iterative decoding. And he has his own company and has done a lot of great work. And today he's going to be talking to us about quantum coding. And as he was explaining to us before we turned on the recording, and I'm very excited, he is going to do it from the perspective of people who are well-versed in classical coding and gently introduce us to the quantum constraints. So it's a perfect talk for our research group as a first look at quantum coding. Yeah, and I'd like to also welcome our distinguished guests, Michael Tanner and Dariush Divsalar. So with that, I'm going to go ahead and Bane, I've allowed everyone to share their screen, so maybe you can share your screen, and I'll turn it over to you. Thank you, Bane.
Thank you. So I'll try to share the screen, and I don't know which screen to share. So let me just first start my presentation. Just a second. Okay, so hopefully you see now the right screen.
It's up and it's beautiful.
I'm trying to arrange you so that I see you also. So thank you very much for inviting me to give this talk. The talk is about trapping sets and iterative decoding for quantum LDPC codes. And I guess there are a couple of messages that I want to send here. One is that there are a lot of things that as classical coding theorists we can offer to our quantum colleagues. Many of the problems that quantum physicists consider are relevant, and sometimes they don't consider some of the engineering aspects that we know how to solve. So with that, we have started working on this on quantum LDPC codes a couple of years ago, and there are many things that we understand. There are many things that we still don't understand, and I enjoy giving talks in which there are many things that I don't understand. So hopefully this will inspire us to discuss and clarify. So we published these results in my first quantum journal. And this is also put on archive, so you can see the details of this work. So, but let's start with the question why quantum LDPC codes are important and what makes them attractive. So typically qubits in quantum computers are organized in this rectangular array, so they are physically placed on a rectangular array, and there are devices that allows, or quantum gates that allows them to interact. So of course we want them to be stable, so, and we want to protect them. So what we do is put these parity checks so the circles represent these qubits and these squares represent checks. So there is a very specific way of what these checks are, but I will skip this for later. So they're related to what are called stabilizers in the code. But for us, it is not important at this moment. So this would be a typical typical code that is used in quantum, would be used in quantum computers, and many companies are building such computers. So the LDPC codes are, quantum LDPC codes are really a generalization of this. So we now allow interaction of these qubits that are not very local, so qubits at different positions can interact now. So what we do is we represent this as a Tanner graph, but kind of a double Tanner graph when we have two types of checks. One checks we will call X checks, and other we will call Z checks. This, of course, comes from the fact that later on we will introduce poly groups, and that errors in a quantum system will be poly errors, will be some poly operators that act on our qubits. So this X would be equivalent to bit flips or qubit flips, and Z errors will be equivalent to phase flips. But so our alphabet really in quantum is quaternary, and there will be different two types of errors really, and combination of these two types of errors. But for now, we just consider that there will be we consider this graph when there is a two sets of disparity checks. So you see immediately that this introduces some constraint of how these codes are designed, and also you see that there will be constraints on how these codes are decoded. Of course, we are interested in iterative decoding of this. So lately, this year and past year, there has been a lot of papers on quantum LDPC codes, and there are reasons for this. So first of all, we know that they can be efficiently decoded using low complexity algorithms. And imagine you would like to use LDPC codes in quantum communications, but also in quantum computers. And by the way, we are pretty far away from using codes of sizes that we use in classical communication, like 1,000 bits. So there are technical obstacles to do this, but it is of great theoretical interest, and these are a list of reasons for that. So remember how these stabilizers, these red and blue squares were arranged. They don't interact, they don't involve too many qubits. So they have bounded and low weights. There is this theoretical work by Gottesman that they promises fault-tolerant computations with constant overhead. And there has been a lot of papers, really, not only the last year, but in the past on different constructions of LDPC codes. And maybe we can leave this for some other talk. So, but last year was pretty important because Pantalev and Kalachev, two researchers from Lomonosov University in Moscow, show that you can construct quantum LDPC codes with a minimum distance that increases linearly with the length of the code. This was a big achievement because it was believed that the minimum distance could grow only as a square root of the length. This paper is interesting because it uses very similar arguments that we used earlier to show that LDPC codes can correct linear fraction of errors. They use expander arguments. So when you look at these papers, there is a lot of flavors of previous proofs that are using classical. So this ignited interest again in quantum LDPC codes. So now as I said, quantum physics, typically what in quantum literature you see is that these codes are decoded by belief propagation. And just by looking at this graph that you just show with these two parts in the Tanner graph, you can, or, this array, rectangular array, you can see that message passing algorithm and belief propagation algorithm is not going to work very well, because there are cycles in the Tanner graph, and then of course this is not good. So now of course it is interesting that of course when we implement these algorithms, we will use some kind of a simpler algorithm, maybe bit flipping. There is algorithm by Tillich and Zemmour that is called the small set flipping algorithm. So they have flavors of bit flipping algorithms, and these algorithms again will make this error floor or convergent performance worse. And of course, when we implement iterative decoders in practice, there will be, of course, they will be implemented by in finite precision, and we know that this will also make the performance bad. So,
Bana, I have a question. We cannot directly measure the observation because we destroy the quantum state, but there is an indirect generation of syndrome.
yes, I will come to this.
That's what you're using, syndrome type decoding.
Yes, I'll come to this just in a second. Yeah, so this is basically the main discussion of our today. So we want to do decoding, but just because we can observe only a syndrome. So this is what our decoders are.
And is it possible to eliminate loops, length fourth loops or not?
Yes, it is possible, and I will also talk about this. So it is, so this, so there are a couple of constructions lately in last 2 years that actually start with classical LDPC codes and construct quantum LDPC codes to make them sparse. So this definition of sparsity is now different. So in some cases, it doesn't mean necessarily that you eliminate all 4 cycles. In some cases, you eliminate 4 cycles and you have 6 or 8 cycles. So, and these codes are known, and but you will, as you will see later, they also have dense configurations that will cause this error flow. So coming back to this.
Hi, Bane, this is Lara. Sorry.
Hi, Lara.
Yeah, hi, this is wonderful. Thanks so much for taking the time to present this. Can you maybe educate us on what is quantum LDPC? How is it different from LDPC?
I will.
Okay.
Yes. So, so in any case, I just want to tell you also about iterative decoding algorithms. So, and what was known for iterative decoding, what is used now for iterative decoding. So, first of all, there are, the short answer to this question is that depending on the type of error model that you consider, the decoder of a quantum code is not different than decoder of an classical code, except that it is a syndrome decoder. So now, but the structure of the code will impose some additional constraints, and you will see these constraints later. So now what people have done is in quantum literature is the following. So first of all, I just illustrate this on one of these storic codes. Storic code is this, this rectangular structure when you wrap it around horizontal and vertical axis. And then you run a belief propagation. You see, I think for this audience, it is not necessary to explain that this is not going to work well. And these are kind of performance that you will get. So this would be bit error rate, and this is the performance that you will have in the code word error rate. So
It's the graphical structure forms the surface of a donut.
yes. So now what you do, what is a common thing to do is to do order statistics decoding. So first you run belief propagation, it fails, and then you find reliabilities of bits, and then for bits that are least reliable, you do Gaussian elimination. But you know that order statistics has complexity that is cubic in dimension of the code, so this is pretty complicated algorithm. So what? And these are, but improves the performance. And these are
Bane, sorry, that's something that Hung Jae and I are particularly interested in. Is there a good paper that is like a place to reference for that ordered statistics decoding is cubic in the dimension of the code?
Yeah, so this paper by Pantalev and Kalachev actually is a good reference. So there are two papers by them, one where they prove linear distance, and then there is a previous paper where they talk about different types of codes or code construction. So they use actually order statistic decoding. So the reason
sorry, question, is this the code length here?
yes.
So,
yeah, so
these are
these are very low rate codes. So and there will be even lower rate codes. So we are not talking about, we are talking about rates, I don't know, 1/10, 1/100, extremely low rate codes.
And that is of practical interest at the moment.
So yeah, so these are you will see there are constraints in code construction that make dictates these low rates. So these codes, I think that these codes will be of importance of practical significance in future applications. I don't think that technology is ready for codes of that length. Especially for quantum computer, you would be surprised to see what is really possible to build in the lab. So when I ask my colleagues, what kind of, let's do some experiments, what kind of codes you can really construct and what kind of simulations we can do, this is very far away from what is possible now. But remember, LDPC codes is the only class of codes that is shown to permit fault-tolerant computation. And remember, we had papers earlier in classical literature where we showed how bit flipping algorithm is fault-tolerant, even the gates are faulty. So the similar things exist also in quantum literature. So this is why LDPC codes are of such significance.
Bane, can you just give us a hint, like today in the lab, what a real block length would be that they're working on? Is it 10, 100, 1,000?
So no, I don't think that anybody has implemented LDPC codes in the lab. So the codes that are implemented in the lab, as what I know, are of lengths of let's say not more than 10 bits.
Okay.
So this is where we are.
But it's, I guess it will be clear to everybody if you can provide the structure of
Yes.
H matrix.
Yes. So I'll
the constraints, so people can find out that what's the difference between the classical and quantum.
Yes, so we will do all this, but I'm realizing that it is not going to be just in one lecture. So I'll be happy to give part 2 of this.
Excellent.
Okay, so in any case, let me just skip over this and then just start with the structure. Okay, so you remember how we talked about 2 types of errors, about these X errors and Z errors. So I'm going to forget for a moment about this, and I will consider this parity check matrix that will have these two parts, X part and Z part. So these rows of this parity check matrix will be linearly independent, and these two components. So there will be both of m times m dimensions of m times n, but they have to satisfy this constraint. So this answers Dariush's question. So any quantum LDPC code that is based on stabilized formalism, I will come to this later, will be built on these two. It will be built as through these two matrices, and they have to satisfy these constraints.
Are the two matrices HX and HZ, do they share the same dimensions?
Yes.
Are they both square?
No, they are not square. M is smaller than n.
Okay.
And because oral rows are linearly independent.
Well, M and N are the dimensions of the overall H.
No. So M is dimension, vertical dimension, and N is dimension on the HX and HZ. So the length of H, the horizontal dimension of X is 2n.
Oh, okay. Well, maybe there's a typo. So it's like the M by 2n binary.
Yeah, and it is not a typo. It is because we have these other squares. So these n's are number of qubits, but I represent these qubits in a special way. But I guess I'll come to this later with the explanation of bits. So for now, imagine that we have a code of length 2n. And that it satisfies this. The blocks are m by n, and the total length is 2n, and these two blocks have to satisfy this constraint. So this is
the binary matrix.
These are binary matrices.
Yeah. Okay.
Okay. So as we said, we cannot measure directly quantum information. So there is nothing that is coming from the channel. So the only thing that it is possible to do is to measure a syndrome. And this is also something that requires explanation. But what we will assume is that the channel is so-called depolarizing channel. So there are really two channels. One operates on this part, on the first part of the code word, and makes errors EX. And there is another binary symmetric channel that makes errors on the second part of the code word. So this is the error pattern, and our job is to find error pattern. So we observe the syndrome, and we need to measure the error pattern. So that's all for now. There are things that we need to explain how we get the syndrome, and then let's proceed. So now let's consider a simpler case when we arrange this parity check matrix in this way. So the first part will have this HX and zeros, and this will have, the second part will have zeros here and HZ. So you see there will be parity checks that correspond to only, that are detecting Z errors, and there are parity checks that detect X errors. So now when you look at the previous condition, this condition, you will see that it reduces to this, that X times HZ transpose is 0. Okay, so these are so-called Calder-Bernstein and Shorenstein codes, and we are going to talk about this type of codes. So now these again will be sparse codes, and how we construct them we will discuss later. But whatever we do, they have to satisfy this constraint. Okay, so any CSS LDPC code, it will satisfy this constraint. And by the way, since you ask about good literature, there is of course a paper by Mackay, old paper by Mackay, where he introduced sparse quantum LDPC code. So he discusses both constructions of this type, and these are called bicycle codes and generalized bicycle codes. And these are codes where he used combinatorial designs to different sets to construct. So these things are known how to construct. But my point is, what I want to discuss are decoding algorithms. So again, now you see what is happening here. The situation is very simple. I have two matrices, Hx and Hz, that satisfy this very special constraint. You know, errors, X errors and Z errors act independently. So parity checks, of course, detect each type of error. So you see that I can run two decoders independently, one correcting X errors and one correcting Z errors. This is part of EX and EZ. So my decoding problem reduces to decoding on two binary symmetric channels. And but there are now things that now some specific things that comes from this constraint. So if you look at this constraint, now let's assume for a moment that Hx and Hz are equal. So it is okay to assume this, because if both type of errors have equal probability and have same statistics, I can correct them you know, independently, and there is no reason not to assume that they are independent. And by the way, it will simplify our understanding. Later on, we can generalize this and consider the case when they are not necessarily independent. Okay, so if you look now in the case when they are independent, you see this constraint here means something very special for us. You see that H, so this H itself looks like a generator matrix of the code, because this constraint, this G times H transpose is 0. So this means that actually code H is dual containing. So the code words of C include the row space of H, but they also include some additional to the L code words. And of course, this number of code words depends on the dimension. So this G has rows of H, but it contains also some additional rows. So this will be very important later on for us to understand type of errors that we make. So now, here is one example. This is a string code. So this is generator matrix, and this is a parity check matrix. And as you can see, H parity check matrix is contained in the generator matrix, and parity check matrix has all rows of even weight. And in the generator matrix, the last row has odd weight. So now, when I look at in the code, so I see that there are two cosets in the code. So one coset will be cosets with even weight, and the one coset will be with odd weight. So now this is what quantum code is. So the quantum code is not defined as a sequence or a collection of code words. It is defined as a collection of cosets. So this coset here is going to represent some quantum information, and this other coset is going to represent other information. So I can assign these to these code words to logical 0, and I can assign to these code words, classical code words, if you wish, to logical 1. So this is what it is. So the quantum code I define as a subspace of a vector space, and the idea is that when we add errors, we move one space subspace to another. So this is important to keep in mind, because this defines dictates how I define the decoder for a quantum code. Okay, so what classical syndrome decoder would try to do is to find just an error pattern that explains best the syndromes. It will try to find one error pattern that will match the syndrome. In quantum decoder, it is not unique. Any error pattern that will match the syndrome, but up to the raw space of H, within the coset, will be a valid error pattern. So in other words, let me just read this. So what my decoder will do is it will accept as an input syndrome, and it will try to find an error pattern. Most likely, of course, we are looking for a low weight error pattern. But error patterns that are E, actual error pattern, plus row of H will be also a valid output of my decoder. So, and this is also something to explain. So this is what is quantum in the code. So you see, on one hand, the decoding part is easier because I don't have to produce. I mean, there are many valid outputs that of a decoder. So there is, this, different error patterns up to this addition of H. But on the other hand, the decoding is more difficult because I don't have channel information from the channel. I have a syndrome. So these are kind of two things to keep in mind. So, all right. So now let's. There are many things that, of course, we haven't clarified, and that comes from the quantumness of the channel. So, what is depolarized channel? What X and Z mean? Why the parity check matrix have n columns? So, what is the quantum origin of this condition? Then what Rick, you ask is about code constructions. Then also constraints of the low weights of H do implementation, the dependence of the structure to D mean. So why is E valid decoding algorithm? So we also want to discuss miscorrection in the general case of this. So, and then of course, quantum patterns, how it is possible to obtain a syndrome without disturbing a quantum states. How do we measure a syndrome? What are the stabilizer codes that I mentioned? And how we construct quantum LDPC codes from classical ones. So these are, you see, all the, very important questions that we cannot answer in one talk. But I'm aware that we have to answer, and I'll have these slides for later. But now, let's summarize the problem that we want to consider in this trapping set question. So we are given generator matrix and parity check matrix, and we observe a syndrome S. Remember, we will be decoding just one code, one classical code, and we want to find this find the error pattern that matches the syndrome. So H will be parity check matrix of some LDPC code that we know how to construct. And then we decode by using iterative message passing decoder. So no order statistics, nothing. So now what happens in this case? So you see, you can also ask this question very classically. So it is a syndrome decoder, and what are trapping set of a syndrome decoder? So there is complication, and I know that I'm repeating this. There is also this complication that comes from the quantumness about what is a valid output. So, we want to find trapping sets of iterative syndrome iterative decoders with this additional constraint on what is valid output of the decoder. Okay, so now as we know, whether the decoding algorithm produces a valid correction vector depends on the weight of the error pattern, of the minimum distance, but also on the decoder. And we know that there will be some graphical structures that will prevent iterative decoding from converging. And these structures we refer as trapping sets. And as we will show later, error floor is attributed to these dense subgraphs. So there are now some surprising, so this is actually what we are trying to do. We are given tunnel graph, and we are there are errors that we, of course, we try to find, but we cannot observe them. So what we observe is this is the syndrome. We know what parity checks are not satisfied, and we want to find error pattern. We want to find these red variable nodes that will match the syndrome. So red means the 1 and white means 0. So any, but the point is that any arrangement, any of this coloring of circles in red that will match this syndrome, that it will satisfy this condition that I mentioned, will be a valid answer. Okay, so you see what, so first of all, I think it is not easy, not very difficult for us to convince that we can, for this, that we can use message passing algorithm, and that that our decoder will initialize channel value as all 0 code word. By initializing channel vector as all 0 code word, we are going to converge to low weight error pattern. So you see, I am not going to produce code. I mean, I am not trying to detect or produce a code word, and my decoding algorithm is going to produce error pattern, low weight error pattern, because it is most likely. So this is what we will do. And again, for this audience, I think we all understand that how it will work. So any iterative decoder will also fix values of check nodes that are not satisfied. So we are not going, and we are trying to find an error pattern that will match this syndrome. So the iterative decoders are really old-fashioned iterative decoders, where we fix the value of the check node, and when where we initialize channel values to 0. So it can be Gallagher B, it can be bit flipping, it can be message passing. Any of the algorithms that we use could be used in this setting.
But Bonnie, I just want to clarify. So you don't have any information about the channel nodes, but you do have information on the check nodes, but you don't have likelihoods. You only have like sort of 1s and 0s.
Yes.
And it seems like there were some like algorithms that find stopping sets. I'm having trouble. Yeah, Bane Hashimi, where I would think you could like just send out a 1 to any node, and if you don't get any collisions, you're done. You found a low weight error word. But if you get a collision, the collision needs to kick it back to the check node, and it needs to go somewhere else.
Yes, yes. So you see, there is nothing really special about the algorithm. You see, the algorithm itself. First of all, it is a binary symmetric channel, right? But we don't have channel information. So we are trying to find just an error pattern. And we have syndromes. So we want to match syndromes. So that's all that we have to do. So it is a trivial modification of any algorithm. So we don't have soft information. Talking about this, by the way, we recently submitted a paper where there is a special type of channels where you could get soft information, but it is more complicated. It is something that we cannot discuss. But there are cases in quantum where you can get soft information. It is not topic of our discussion today. So in any case, so now what happens? So I can the way we can find trapping set is, of course, by simulations. Remember, Nitin has this software where we can actually search for trapping set very easily. That you guys did also a lot of work on absorbing sets and special type of trapping sets. So all this is applicable now with these constraints of that it is a syndrome decoder, and that what actually means to find a error pattern. By the way, minimum distance of these codes that we will use will be very large. So it will never happen that we converge to some code word in this generator matrix that I showed, and I denoted by L, that is not, that is pretty bad, right? So that we make miscorrections. So when we run simulations for some reasonable probabilities of error, as usual, these miscorrections never happen. So the decoder mostly fails because it doesn't converge to a code word, because it is trapped in a trapping set. But now what is really fun is that these trapping sets are now strange. So I will skip these simulations. I was giving a talk in Ken Brown's and for Ken Brown's group. So I prepared this for physicists, but I will skip illustration of Gallagher B. So, and I'll just tell you what we found. So we found two types of trapping sets in quantum codes. One type is classical looking trapping sets, just regular things that we show in classical codes. And there are some trapping sets that we don't see in classical codes that are inherently trapping quantum. So, and you observe these trapping sets inside code words. So here is one structure that illustrates 10,0 trapping sets, which is a code word. So now let me, and then for some codes, for this code that is called hypergraph product codes, we did analysis and we found, we basically enumerated all relevant trapping sets, and you can see these are these classical looking ones, and then there are again no assumption of what is harmful or what is not. So these are something that you recognize, and some of them are elementary, some of them will be non-elementary. But let me show you what effect we have in this quantum. Maybe it is better if I show this picture to explain how this other type of trapping set appear. So imagine now that you have this code word, and imagine that you observe a syndrome and that all checks are not satisfied. So that all checks in this that are black are 1. So, and then you don't have any channel information, and you are trying to decode. So you see that there will be different error patterns that could be solution for what you observe in a syndrome. So this is one error pattern that will make all these checks not satisfied. And this will be another error pattern that will make all these checks unsatisfied. So since you have, and I think this is kind of the key thing in my talk. So we are trying to match the syndrome, and there will be different error patterns that are competing to be a solution for this. We don't have soft information, and in this case, because of symmetry, you see that the message passing, that belief propagation or any algorithm is going to propagate messages, but because these two error patterns are equally likely, what the decoder will do is will oscillate between these two error patterns and will never converge to either one of them. So instead, it will produce output where all of them are, when all variable nodes are declared to be in error. And this is, of course, not a solution. Because this is not a solution because it doesn't match the syndrome. So instead of producing either red error pattern or blue error pattern, it will produce one big error pattern that is really, that is not going to match the syndrome. So this, and by the way, this effect was observed by many people in small examples, but this is actually what is happening. So what is bad for quantum codes where we have these symmetric structures, symmetric code words. So you see that there will be other types of symmetries in the code word, but when we have a code word and we can find symmetric structures like this is going to produce for sure a failure of you see any iterative decoder. So
Bane, that's not, so what you're describing, so there's a red solution and a blue solution. And if you happen to get to those solutions, you'd know you had found a right answer.
exactly.
But instead, the way the iterations work, you actually light up all the variable nodes.
Yes.
And in each iteration, you can't shut any of them off, but you know that you don't have the right answer.
Exactly. So you just don't converge. You oscillate, and you met in the first iteration you didn't match the syndrome, and then you are just progressing and you don't converge. So that's
there are, in the classical error pattern or error floor mitigation techniques, like Olga Milinkovic and has studied like using a slower convergence pattern or an asymmetric convergence of different edges that is able to overcome some previous, some trapping sets in a classical sense. And we've also done similar things with machine learning to adapt like the weights on edges. Would those kinds of techniques, have people tried those things?
No. So this is why I'm giving this talk to you guys, because you see that many of these things that we have done will be very effective in this. And so in our paper, in our quantum trapping set paper, we just provided some illustrations of how some of these techniques will work, but we haven't. So Nitin is working on these algorithms, but it is far from being explored. So there are many of these things that can be used, and I will show you actually how it improves the performance. So obviously.
Bane, when you're talking about trapping set, are you that includes also absorbing sets that Lara introduced?
So you probably see from my talks and the approach that we have in my lab is that we don't define that we don't define a trapping set combinatorially, and we then investigate whether they are present in the graph or whether they are harmful. We define the trapping set only if they are harmful. So the trapping set that I define, I don't assume any prior structure of the trapping set. I only thing that I use is a knowledge of a parity check matrix and a decoder. So this will dictate what trapping sets are. So, and remember, so what this trapping set structure is another question. And I think there is a lot of nice things that can be done in studying code words and symmetry of code words in LDPC code. Finding what, obviously these symmetries, I think it is clear from, from experience that we have, that these symmetries, if I just run a flooding schedule, that this will produce a trapping set. There is also what Rick says, a lot of nice modifications of the algorithms like sequential decoding or layer decoding that will obviously solve this problem. So far we don't have characterization of trapping sets in terms of this parameterization like A, B, and so we of course use A and B just because of historical reasons, but we don't imply what would be dangerous or what is not. So, but there is there are also some new problems that I'll show you that are very that are I don't know, curious and new. So let me just
sorry, can I ask a question?
yes.
So you mentioned earlier that this specific trapping set comes from the stabilizer properties of the quantum codes. Does this imply that, because I thought that we could just use any LDPC code as the LDPC, but it seems that there's some constraints based on the quantum nature. Is this, yes?
So, yeah, actually, let me show you, skip a couple of slides,
Yeah.
and maybe go to the end of presentation and show you some constructions of LDPC codes that use classical codes and how this affects the structure of an overall code. Let me, so these are all different things that I will skip, and these quantum things that I go, and then
if you could post this, that'd be great, so we could look at this ourselves
Sure.
later.
And we are coming close to the end of our hour, but
Yes.
it does look like we're going to have, it's actually, you've been renewed for another season. So we're going to have a sequel.
So let me show you what I find the most interesting thing to consider. So Tillich and Zemor show that you can construct, that starting from any two classical codes, you can construct a quantum code. And this is how you do it. You start with two codes, H1 and H2, and you construct this HX and HZ in this way. We don't have to understand now what it means, but I just want to show you what actually happens. So you have one Tanner graph and another Tanner graph, and you kind of take pairs of variable nodes, pairs of checks, pairs of variables and checks, and you connect them to this X and Z. You connect them through, you put edges in this, and this is how it is, how it ensures that we have this quantum property. But and here is the structure of parity check matrices when you start with this code. So these are, these are not sparse code. These are some Hamming codes. It doesn't matter. It's just for illustration to show what kind of structures we get in the in HX and HZ. And remember, we will be decoding HZ and HX separately. So you see what happens. So depending on the column weight of the code, there will be actually in the Tanner graph of each of these matrices. Okay, let's just imagine that I use Tanner graph 3,5 regular Tanner code as a basis for my construction, this hypergraph construction. So remember, there will be these Kronecker products. So what I will have is I will have graphs that will have, I will have variable nodes that will have degree 3, and then on the other side I will have variable nodes that will have degree 5, because I take transposes. If you see here. So I come to another type of very interesting codes that are irregular but have only 2 degrees. So if I start with a regular classical code, I will have a quantum code that will have only 2 degrees. Variable nodes with only 2 degrees. And now this interaction of messages and passing messages between these two graphs that will have different degrees introduce also very different dynamics of message passing. And this is also something very interesting to study.
Okay. So Bane, we're going to end up losing a big chunk of our audience. So is there a way for you to sort of bring things to take us to intermission, and then we'll set up an additional seminar for you to continue. I really am so grateful for this.
Yes, that would be great. Thank you very much.
Yes, I realized. So let me stop sharing. So I realized that it is will be, people have working on this for a long time, and it is, there are a lot of details, but I I really see that there are a lot of things that we can do together, and that some of these problems are familiar to us. So I thought that I start with this, and then we can maybe talk about these special constructions, and also, you know, these constraints, quantum constraints or on code constructions.
Sounds great. I'm already excited about the idea, since we have sort of we've set up a factory, you know, to apply machine learning to the graphs, especially small graphs, to get them to converge. We could easily, you know, if you have a particular code and you'd like to see what can machine learning on the weights of the edges do to eliminating the trapping sets, we could sort of do that as a first collaboration.
So see, one very interesting thing when you observe this, so you know how you define a trapping set in classical case. You take variable nodes and then you find the graph that is induced by them. If you do this, from example that I show you, you're not going to get a connected graph. You will see that these variable nodes have just check nodes that are 3. So if you observe this, you won't be able to even start defining trapping sets. So you see, there are many things in a definition of trapping set that needs to be changed. So, you know, I have to expand from check nodes, not from variable nodes. So there are, you know, these non-trivial kind of things that also need to be defined when we talk about trapping set, when we discuss also finding them, you know, and using this knowledge for decoding.
Very exciting. All right. Well,
thank you very much for your attention. I mean, hopefully I didn't disappoint you, because the talk starts with the classical things, and many of these things we haven't defined, these quantum things. So, but maybe we'll do it next time.
well, it's, you know, we're walking around the elephant, and you showed us the tail and the ear. And next week we'll take a look at some of the legs and the back, or not. Actually, I think we're gonna, this seminar series runs every other week. So we'll be in touch about, like, I have to check and make sure what's happening 2 weeks from now, but maybe if you're available 2 weeks from now, we might have a second talk then. Okay.
Yes, I'll check. I think I am, but we will.
Well, thank you very much, Bane.
It was good to see you all.
Thank you. I'm going to stop recording now.